Students often seek a deeper understanding of the various concepts in physics. From classical mechanics to quantum theory, it offers insights that illuminate phenomena ranging from everyday occurrences to cosmic events. Study of physics not only enhances scientific literacy, but also fosters critical thinking, enabling students to explore the captivating interplay between matter, energy, and the fundamental laws governing our reality. So let us explore the world of physics now.
Dear students, in this video we are going to study about power in an AC circuit, what full and what less current, power factor, advantages and disadvantages of alternating current over direct current. Now let us consider power in AC circuits. Introduction. What is power of a circuit? How will you define that? Power of a circuit is defined as the rate of consumption of electrical energy in that circuit, and it is given by the product of the voltage and current. In an AC circuit, the voltage and current vary continuously with time. Let us first calculate the power at an instant, and then it is averaged over a complete cycle. The alternating voltage and alternating current in a series inductive RLC circuit at an instant are given by the expression V is equal to Vm sin omega t and I is Im sin omega t plus phi. From this expression you see that the current has a maximum value of Im and the voltage has a maximum value of Vm, and this phi is the phase angle between the voltage and current. The instantaneous power is then by the product of voltage and current, that's given by Vm Im sin omega t sin of omega t plus phi. Vm Im sin omega t cos phi plus cos omega t sin phi, and therefore the expression for the power is given by Vm Im into cos phi sin square omega t plus sin omega t cos omega t sin phi. So the average of sin square omega t over a cycle is half, and that of sin omega t cos omega t is 0. Substituting these values, we obtain the average power over a cycle as Pm is equal to SP average power equal to Vm Im cos phi into half. That can be written as Vm by root 2 Im by root 2 cos phi. This average power is given by Vrms into Irms cos phi, as Vrms is given by Vm by root 2 and Irms is given by Im by root 2. So the product Vrms and Irms, that is called as apparent power, and cos phi is called power factor. The average power of an AC circuit is also known as the true power of the circuit. Now we will consider the special cases. For a purely resistive circuit, the phase angle between the voltage and current is 0, and therefore cos phi will become 1. And hence the average power is given by Vrms into Irms, product of RMS value of voltage and RMS value of current. And for a purely inductive or capacitive circuit, the phase angle is plus or minus pi by 2, and therefore cos plus or minus pi by 2 is equal to 0. Hence the average power will become 0. Next is for series RLC circuit, the phase angle is given by phi equal to tan inverse of x minus xc by r. So the average power is given by RMS value of voltage, RMS value of current into cos phi. And for series RLC circuit which is at resonance, the phase angle is 0 and cos phi becomes 1. Therefore the average power is given by the product of RMS value of voltage and the RMS value of current. Now let us study about what is current. For that, let us consider an AC circuit in which there is a phase angle of phi between the RMS voltage and the RMS current. The voltage is assumed to be leading the current by a phase angle of phi, which is as shown in this phasor diagram. So this is IRMS and this one is VRMS, and the phase angle between them is about phi. So here you can see that the RMS voltage leads the RMS current by phase phi. Now IRMS is resolved into two perpendicular components, namely IRMS cos phi along VRMS and IRMS sin phi, which is perpendicular to VRMS as shown in this 4.51. So here you can see that this IRMS is taken along the x-axis and this VRMS is making an angle that is about a phase angle of phi So this IRMS is resolved into two components. One is along this direction, that is IRMS cos phi, and the other component is IRMS sin phi, which are perpendicular to each other. And this component of current, that is IRMS cos phi, so here this IRMS cos phi, which is in phase with the voltage, is called the active component. And the power consumed by this current is given by VRMS into IRMS cos phi, and therefore it is called as watt-full current. And the other component, IRMS sin phi, which has a phase angle of pi by 2 with the voltage, that is called as a reactive component, and the power consumed is 0. Therefore it is called as wattless current. And this current in an AC circuit is said to be wattless current if the power consumed by it is 0. This wattless current occurs in a purely inductive or capacitive circuit. Now let us see what is power factor. The power factor of a circuit is defined in one of the following ways. You can see these 3 points. The first one, power factor is given by cos phi, and that is cosine of the angle of lead or lag. The power factor is given by R by Z, where R is the resistance and Z is the impedance. And power factor is also obtained by this expression, that is average power by VRMS into IRMS. It is called as true power by the apparent power. Now, what are the examples of these power factors? They are given here. The power factor is equal to cos 0, that is equal to 1 for a pure resistive circuit, because the phase angle phi between voltage and current is 0. Power factor is equal to cos plus or minus pi by 2, and thus also equal to 0 for a purely inductive or capacitive circuit, because the phase angle phi between voltage and current is plus or minus pi by 2. The power factor lies between 0 and 1 for a circuit having RLC in varying proportions. Now let us see what are the advantages and disadvantages of AC, that is alternating current over the direct current. There are many advantages as well as disadvantages of AC system over a DC system. Now let us see the advantages. The first one being the generation of AC is cheaper than that of DC, direct current. And when an alternating current is applied at higher voltages, the transmission losses are small compared to direct current transmission. This alternating current can also be easily converted into direct current with the help of devices called as rectifiers. Now let us see what are the disadvantages. The alternating voltages cannot be used for certain applications such as charging of batteries, electroplating, and electric traction. At high voltages, it is very much more dangerous to work with alternating current than direct current.
In a DC circuit, power is simple, voltage times current. But in AC, the relationship is a bit more rhythmic. Because voltage and current fluctuate, we look at instantaneous power and average power. Average power depends on VRMs, ERMs, and the cosine of the phase angle. Ever wonder why some components draw current but do not actually consume energy? This is wattless or reactive power. In purely inductive or capacitive circuits, the phase shift is exactly 90 degrees. Energy flows into the component and then right back to the source. Think of active power as liquid, reactive power as foam, and apparent power as the whole glass. So, why did AC win the war of currents? Efficiency and distance. AC steps voltage up easily with transformers, cuts transmission loss at high voltages, and uses simpler motors and generators, while DC step-up is complex, losses are higher over distance, and brushes wear faster. Step up voltage, drop current, and you minimize heat loss over hundreds of miles. From the lines over your head to the wattless energy keeping motors spinning, AC remains the backbone of our modern world.